Okay, thanks a lot. Sorry that I was not able to join the meeting in person, but I am excited to share some of the results we have from this project that I have been undertaking in collaboration with Nick Schmer and Matt Sigler. Um, so I'm going to talk about the seismic signature of ice distribution, specifically at the lunar South Pole, but also sort of generally. You can go on to the next slide. So, we've heard a lot. From other talks at this conference about ongoing efforts at lunar science. I think most of the people here probably agree that this is going to be a big decade for lunar science. That means more robotic missions, more boots on the ground, more data, and having a real long-term scientific industrial footprint on the moon is going to require water. And one of the ways that we've been starting to think about how to prospect for water on the moon is using the toolbox that we use for resource prospecting here on the Earth, the toolbox of near-surface geophysics, and that means active seismic surveys, GPR, electromagnetic, um, and in addition to just collecting that data, we need to have the right models in order to interpret the data correctly to have a good idea of what it is that we're imaging in the subsurface. And the way that we do that is with rock physics. Go on to the next slide. So rock physics is a field that essentially relates the structure and properties of rocks and geological materials to their geophysical behavior. And so here is just sort of a demonstration of two typical rock physics models that are meant to demonstrate how, mixtures of rock and ice can have dramatically different physical properties depending on not only how much ice is mixed in, but also where the ice sits. You would have a very different behavior expected from a soft ice supported structure versus a grain supported structure that has free ice sitting within the pore space. And so understanding the way that ice sits is really important for understanding how to interpret larger scale geophysical measurements. Go on to the next slide. Um, so here is an example of a number of different rock physics models, those Voigt and Roos models that I was sort of systematically representing on the previous slide, and some other models, the Hasheen-Strickman model, Voigt-Roos-Hill, which is a sort of averaging of the Voigt and Roos models. But this sort of shows how you can use these different rock physics models to relate. Here, K is the bulk modulus, mu is the shear modulus, but the physical properties of these ice rock mixtures to a given ice fraction, or the percentage of the pore space that is filled with ice. And these models right now are made for a porosity of about 35%. You can go on to the next slide. But in order to constrain what the best model to use to understand these things are, we've been starting to do some in situ microtomography measurements of regolith analog mixtures with ice at the Advanced Light Source at Lawrence Berkeley National Lab. And so we've made a chamber that is capable of getting a relatively reasonable approximation of lunar surface conditions to actually image the samples at in situ conditions. If you can move on to the next slide, we have a picture of the actual vessel in action. It's more or less a vacuum tube that we. Sorry, I lost my slides. Well, the system is a vacuum system with an X-ray transparent external vessel and some thermal pucks that are liquid nitrogen cooled. We can get back up there, and you can head on to the next slide as well, if that's possible. So here's a closer look at the schematic. You can kind of see the thermal pucks are the orange bits in there, and the cooling lines are in that light blue. And in addition to being able to do these in situ structural measurements using X-ray tomography, we can also make acoustic measurements that we can use to constrain the physical properties of the materials in there to make a direct relationship between the structure and the physical properties, which is the real goal of the project. Okay. You can click on through. Here is a little animation, if it'll work, of what this data looks like in there. You get this grayscale intensity, which is proportional to the density inside, and you can use that data to examine the interior structure. Another click will show you how we segment the data to look at the intermixture of the grains and the ice and the pore space, and click again. You can see here's this video, which maybe we should skip for time, which will show you would show you a more detailed thing. But let's move on to the next slide. So I guess I won't talk too much about this, but one of the things we're doing is comparing these analog microtomography measurements with nanotomography measurements of actual Apollo soils. The most of the analog materials that are available for experimentation right now are really made to be spectral analog, so it's hard to know whether they're reasonable physical approximations as well. But we've been trying to do a sort of comparison of the grain morphology and other characteristics that would relate the analogs to actual Apollo soils, and actually to a first degree, they do a pretty good job. You can move on to the next slide. So here's a little slice inside, and you can see that we can actually look at some of the better details of what the grain packing and the pore space looks like, where the ice may potentially sit. And these are the sorts of geometric parameters that we can use to build accurate rock physics models in order to understand that seismic behavior better. If you move on to the next slide, we have just another nice animation where you can actually see in one of the more sparse regions the way that the grains are sometimes supported by ice and sometimes the ice is supported by grains, making a pretty heterogeneous structure. And so if you move on to the next slide, the general heterogeneity of the structure led us to sort of favor this Hasheen-Strickman model, which can accommodate additional microstructural heterogeneity, different grain sizes, different coordination of the grains themselves. And in fact, it offers sort of a range of potential ice to elastic modulus values, and we use an average value to build our model. If you go to the next slide, you can see what it looks like. And so down at the low ice fraction, you can see that the shear and compressional velocities are actually, pretty much what have been measured by actual seismic experiments on the moon. And as you get close to 100% pore filling ice, then you get substantially faster velocities. But in the sort of 1 to 10 to 20% ice fraction, which represents sort of the reasonable range, you start to see that there is in fact a reasonable relationship between the ice fraction and the velocity, which gives us good hope that seismic tools could be a good way to take a look at the ice distribution. If you move on to the next slide, the way we set up our model is by taking a thermal model of the lunar South Pole, assuming some thermal parameters, and then running a multi-physics simulation to look at what the thermal structure in the near subsurface of the South Pole would be. So the sort of z-axis here is in meters. So we're modeling the top 500 meters of the regolith. If you head to the next slide, you can see
2-minute warning.
Thanks. How we then use that thermal model as a guide to make these sort of synthetic realizations of what the velocity model might look like. We either put like massive ice in the coldest regions, or allow for a halo of disseminated ice. And in the most conservative of the models, we just take the coldest regions and put a smattering of disseminated ice. And I should mention, even in the highest ice content of these experiments, the the total ice content in the model is only about 7%. So it's not beyond the realm of what we think might be sneaking around. And if you head to the next slide, you can see the seismic synthetic seismic simulations that we run, setting up 81 digital seismic stations and putting a source in the center of the model. We can then take a look at the way that seismic waves would interact with the velocity structures that we dictate through this kind of model right here. And you can see sort of in the top right here is a snapshot of a map view of what the wave field would look like 25 seconds after a source. And if you head to the next slide, this is a little cross-section view of what the velocity structure potentially would look like in our most highest ice content and lowest ice content models. And one of the observations that we've made is that actually, even in the lowest ice content models, the seismic experiments are really effective at finding the location of the ice. And where we have massive ice, it essentially blocks the majority of the seismic energy. And where we have disseminated ice, you have more of a scattering effect. And that is actually a really interesting observation, because I think that it shows that seismic experiments may not only be a way to identify where ice is sitting, but also potentially how much and in what form it is as well. And I think this is potentially a really interesting, powerful tool that we can use not only for exploration, but also in the design phase of things, trying to take a look at specking instruments and designing seismic surveys for the moon as well. Thanks.